Alright, let's take a look at page 242. We're going to continue to try to fill out this chart at the bottom by matching the different graphs. Okay, original function, first derivative, second derivative. Before I forget, because I don't want to make the same mistake twice, you do have a video assignment tonight. It's just one page. Okay, it's going to be a very short one. Okay, just one page, and we're going to do the rest of them tomorrow together. All right, I forget where we left off. I know we did all of number 1, all the graphs. Did we do all of number 2? Yeah, what were they? 15, 6, 14. Okay, so I think I crossed these off. We did 3, we did 6, we did 9, we did 12, and 14, 15. Okay, all of those are accounted for. Let's check out our next one. So for number 3, they're telling us that the second derivative graph is 11. All right, let's go ahead and check out 11. So we'll label this as f double prime. And we're going to try to figure out some information about f of x and f prime. Where do you want to start? How can we pick apart this graph, different characteristics, things to look for? What do you see, Christian?
I believe if, actually, I'm going to say it anyway.
Go ahead.
If f double prime is positive, that means it's concave up.
Is concave when you say it, what do you mean by f of x is concave? Okay, so where is this graph positive? Can you give a... You can.
Okay.
Do you want to? Yeah.
I'd actually like to.
Go ahead.
Can I go...
Look at the initiative. Go for it.
0 to infinity, it is positive.
Okay, so 0 to infinity, f of x is concave up. And then negative infinity to 0 would be concave down. Okay, so it's telling us something about the curvature, where we look like a regular parabola-ish shape or upside down parabola-ish shape. Okay, we're looking at the curvature. Anything else we want to pick apart? I love it so far. What do you think, Nuj?
At 0, the original function seems to have a point of inflection.
Okay, so notice how at 0, you change concavity. You go from up to down. That's our definition of a point of inflection. So x equals 0, point, maybe we'll abbreviate it POI, point of inflection. So we have pips and pois. Possible inflection points, points of inflection. Save me some space from writing them out. Okay, point of inflection. Looks good. Anything else? Yeah.
Like, because it's a line, you know that f prime will be a parabola and f of x will be cubic.
Cubic. There we go. Okay, so this graph is linear. If we go backwards to the first derivative, that would be quadratic, okay, or a parabola. And if we go backwards again, that would be cubic. I like it. All right. How about any information for the first derivative? The second derivative is the slope of the first derivative. So maybe if you take a prime mark away, that'll help you out. You know, how'd you know it's a minimum at 0? There we go. All right, so notice how this is a value of 0. You go from negative to positive. So this is essentially a derivative graph in relation to the first derivative. If you take a prime mark away, you can kind of see how that would make sense. Okay, so min at 0. If we are negative before the x equals 0, that means f prime is decreasing. So decreasing from negative infinity to 0, and then it'd be increasing from 0 to infinity. I like it. Okay, so I think that's enough information for us to kind of pinpoint what's what, especially since we started to cross out some of the other graphs. So maybe we'll start with f of x first. We want to find a cubic graph that's concave up on the first interval, concave down on the second interval. Yeah?
10.
10. How'd you get it? Good.
Because in the positive side it's concave up, and on the negative side it's concave down.
All right.
It
So,
crosses at 0.
okay. So here's our point of inflection at x equals 0. Notice how we're concave down before it and we're concave up after it. All right. So we'll go ahead and list that as f of x. Right, number 10. Let's go ahead and, okay, so we'll cross that one out. We already did it. Let's go ahead and now try to find the derivative graph. So we're looking for a quadratic that has a minimum at x equals 0, and you're decreasing before and increasing after. We have any ideas? Or can we narrow it down at least? Let's see, when I look at 13, here's a minimum at x equals 0. You're decreasing before, increasing after. So that one checks out. But if you look at 10, there's another minimum at x equals 0. You're decreasing before, increasing after. So how do we know which one it is? What's the difference between number 1 and number 13? The x-intercepts. Perfect. Okay? So what we have to pay attention to is probably another detail that we didn't specifically write down initially. So if we labeled this as the f of x graph, and we're trying to figure out f prime, notice how f of x has horizontal tangents at these two spots, which have related x values of -2 and +2. So the derivative graph, f prime, should have x-intercepts at those spots. So it looks like we can ignore 13 because they're at -1 and +1. And number 1 graph checks out. So you might have to go a little bit further. Even though your initial properties or characteristics are correct, you might have to continue to list more to help you out. So we'll go ahead and list this number 1 graph as the derivative. All right, we'll cross that one out. All right, next one is 13. Well, that probably could have narrowed it down for us also because they're telling us that that's a different one. So 13, we'll label this as the derivative. Let's see if we can pick apart original function and second derivative. Can we list some characteristics? Christian?
On f of x, the slope has to be positive from negative infinity to -1.
Negative 1?
-1.
Uh-huh.
And then it's negative from -1 to 1, and it's positive again from 1 to infinity.
All right, so if the slope is positive here, negative here, positive here, how does that relate to either one of those?
F of x slope. Is that right?
Mm-hmm.
Yeah, the slope is negative whenever
So if the
f prime of x.
so if the slope is negative, f of x,
No, that's it.
Decreasing.
f is decreasing. Okay, so decreasing from -1 to +1. Christian said we're negative, and then we're increasing negative infinity to -1, 1 to infinity. Looks like we can list some maxes and mins. Max at x equals -1, because we change increasing to decreasing, positive to negative. And then x equals +1 would be a min. Looks good. Any other characteristics for f of x, f double prime? Good, Addison, yeah. All right, how'd you get negative and positive? Those are great. It's decreasing, increasing. It's the slope values. Good. So the second derivative is the slope of the first derivative. We got to analyze where we're increasing and decreasing. Good. And what was the last one you said? It would be linear. How'd you know linear? All right. So this derivative graph is quadratic. So the second derivative would be linear. So then the original function is cubic. Good. There we go. We can also do, we have an x-intercept at 0, because that's where we're changing negative to positive. So let's see if we can find these graphs. So f of x, we need a cubic graph, max at -1, min at +1. The only other options we have left are on the front. Now the only cubic ones we have left are 2 and 4, and unfortunately they both seem to have a max at 1 and a max at -1. Oh wait, this one has a min at 1 and this min's at -2. So can we narrow it down? Number 2 looks good. Okay, so we'll list number 2 right there. All right, let's go ahead and try to find the second derivative graph. So we need linear. We have an x-intercept at 0, and we are negative before it and positive after. 7, right. These are the only linear ones left, and notice how this one goes through the origin. All right, so we'll go ahead and list 7. All right, now process of elimination, that's going to lead us to the last one. So this is the original function for f of x. Can we quickly jot down which one might be the first derivative, which one's the second?
5 is the first one.
5's the first, how'd you know?
It's quadratic.
It's quadratic, and 8 would be the second because it's linear. Okay, so they do get kind of easier the more you identify. You can kind of do process of elimination. So we'd have 5 and 8. Looks good, guys. We doing okay? Starting to get a little bit more comfortable? Characteristics. They're good. All right, let's go ahead and take a look at a more algebraic approach to this concavity or curvature. Okay, we're going to practice identifying intervals where we're concave up and concave down. And what's really nice about this technique or process is that it's the same exact method that we did with the first derivative. Remember making the sign chart pluses and minuses. We're going to do that same thing, but for the second derivative. Okay, just not the first derivative this time. So they give us the first derivative equation, and they want us to figure out where is the original function concave up, concave down, and where we might have some points of inflection. Okay, so if we're dealing with concavity for g of x, the original function, we're going to have to first of all find the second derivative, okay, how the first derivative is changing. So how might you want to go about finding the second derivative if this is our first derivative? Quotient rule. Okay, so we'll have low d high minus high d low, square the bottom, and we're good to go. Now typically with the first derivative we set it equal to 0 and try to solve, and that's where our critical points would be. But now that we're analyzing the second derivative, okay, in relation to the original function, we're going to set it equal to 0 to help us find those pips, okay, possible inflection points. So let's see if we can clean this up a bit to help us solve for x, find those possible spots. So if we distribute in the negative 12, 6 times 12, is that 72? Okay, and then 9 times 12? 108, okay. All right, and then after the minus sign, we'll distribute in a negative 12x, but we can also distribute in the minus sign as well. So double negative change to a positive, let's just distribute in 12x into everything. All right, combining like terms, we get 36x to the 4th plus 72x squared minus 108. All right, everything's cleaned up. Where do you want to go from there? What do you think, Nish?
If that fraction is equal to 0, then just the numerator is equal to 0.
Okay, so let's focus on the top. How do you want to solve for x? You see it? Yeah.
Back out of 36.
Okay. That's a large number to take out, but we can do it. So x to the 4th plus 2x squared minus 3. Looks good. Can we keep going? Yeah?
You could let like k equal like x squared, and then rewrite that as like
Mm-hmm.
k squared plus 2k minus 3, and then factor that to like k squared plus 3.
All right. So, all right. We're used to factoring if it's a quadratic, right? Power of 2. So if this 4 was a 2 and this 2 was a 1, you could easily factor it. Two numbers that multiply to -3 but add to 2. Since it's a 4, in the factors we would need an x squared and an x squared, because if you do the FOIL process to expand it, x squared times x squared would give you an x to the 4th. So it's still the same factoring techniques that you know, it's just applied to a higher power, but it still works the same way. Can we keep factoring? Is there another method in there? Yeah, where? We have a difference of squares. x plus 1, x minus 1. All right, so let's find these possible inflection points where the curvature might be changing. Is there any x solution for the first factor? Is there a number you can plug in that would cancel out a positive 3? No, because if you square it, it's always going to be positive, right? So this x is not giving us an answer. What about the other two? -1 and +1. Okay, so these are possible inflection points. I call them pips. Now, there was another definition or another part to our definition for a point of inflection or a possible point of inflection. It's where the second derivative is 0 or undefined. Wasn't our second derivative a fraction? Yes. So we have to be diligent and check to see if it's undefined anywhere. So can you think of a number that would make the bottom part be 0? Somehow you'd have to cancel out a positive 9, right? And is there any way you can raise something to the fourth and something to the second and make it a negative number? No. So in this case, there are no possible inflection points. So we have to be certain to check both parts if it's a fraction. Is the top ever 0 or the bottom ever 0? Those are giving us those possible locations. So now that we have these locations, +1, -1, we're going to go ahead and set up our sign chart, just like we've done in the past. So -∞ to -1, -1 to 1, 1 to infinity. This time, though, if we're checking concavity, we're going to analyze the second derivative. All right, and more often than not, I think our cleanup version would probably be the better one to pick out of all of these that we have here. So pick any number you want between -∞ and -1, and we're going to test it to see what the signs are. So if you plug in your number up top, positive or negative? Definitely positive. And notice how the bottom is forever going to be positive because you're squaring the entire bottom. So positive divided by positive is positive. Pick something between -1 and +1. 0, easy. What's the top? Negative. And if the bottom's always positive, that's negative. Something between 1 and infinity. Whatever. Plug it in. Definitely positive. Over positive is positive. Okay, so let's go ahead and list our justifications. G of x is concave up on which intervals? Because G double prime is positive. All right, G of x is concave down on -1 to +1 because the second derivative is negative. Running out of room, so I'll go to the top here. Do we have any points of inflection? Remember, these were possible inflection points. Does our sign chart confirm if they are or not? Yeah. This is a point of inflection and another point of inflection. It's where the signs change. So we'll say points of inflection at x equals -1 and 1 because G double prime changes sign. It's not needed to be specific if it changes positive to negative or negative to positive like we had to be with maxes and mins. It's just the sheer fact that it changes a sign is that it's a point of inflection. So you don't have to be specific, changes positive to negative or anything like that. Right? You see how it's a very similar process? we're just doing it to the second derivative instead of the first. Okay, and that's telling us about concavity. We're doing okay? Good. All right, so what this is leading us into is an alternative way to verify maxes and mins. Remember how the only method we've done so far is to do the sign chart to look for those changes? Now that we have a way to determine concavity, we have an additional method to help us verify maxes and mins. And in most cases, it's actually quicker and easier. And that's what we're going to take a look at here. So this is what's called the second derivative test. Okay, second derivative inferring that we're going to have to look at concavity somehow. So what's important though is we have to first identify a critical point, okay, where we have a potential max or min. So we're going to let that be an assumption. Okay, we're going to say let x equals a be a critical point. Remember, that's our definition for a possible max/min for the function f of x. Okay, we're going to assume that. Let me ask you this. If we were to plug in the critical point into the second derivative and our answer is positive, can we infer if this critical point is a max or a min? If the second derivative is positive, what do we know about f of x? Yeah. Why?
Because if the second derivative is positive, that means it's concave up. Concave up.
When you said it, what do you mean by it?
Oh yeah, wait, what did I say? I'll just restart.
Okay. If the second derivative is positive, then it.
Okay, the second derivative is positive, then the f of x is concave up.
All right.
Which means that there is a minimum because that's just the shape.
There we go. So we already know that this location is a possible max or min. If we can plug in that value into the second derivative and our answer is positive, we know the curvature of the graph is concave up. And notice how that would create a minimum at this spot. So if the second derivative is positive, then f of x is concave up, resulting in a minimum at x equals a on f of x, okay, on the original graph. What's the other case? If the second derivative was negative, then f of x is concave down. So that would result in a maximum at x equals a, okay, on the original graph. What's the third case? Yeah? If it's 0 or undefined. Okay, so if it's 0 or undefined, then f of x has no curvature. So x equals a is not a max/min. Okay. Remember, a critical point is a potential max or min. It might not always be a max or a min. That's why you have to test it. So in addition to using our sign chart process that we are very familiar with, we can now use the second derivative test that might be a little bit quicker, and in some instances this is the only method that you are actually able to use, and I'll show you an example of that tomorrow. Okay, but for now it's going to be an alternative way for us to classify maxes and mins. So let's just kind of see how this one operates. We're going to try a few examples on the back. So use the second derivative test to locate and classify all the relative extrema, okay, maxes and mins where they might be. So we first of all have to find critical points. Where are the potential maxes and mins? So we'll find the first derivative, and we'll set it equal to 0. We also have to check if the derivative is undefined anywhere. Is this going to be undefined at any spot? No, it's not a fraction, so you really don't have to worry about it. So where do you want to go from here to find some critical points? We thinking factor? Okay. Take out a 4x squared. We're left with x minus 3. So our critical points are 0 and 3. Okay. So up to this point, you would create your sign chart, test some numbers, look for positive, negative changes, and you could do your maxes and mins. Okay, you can do that. But let's try the second derivative. So if this was our first derivative, can we go another round? Bless you. 12x squared minus 24x. All right, so we're going to take these critical points and plug them in for the x's in the second derivative. If you plug in 0, you get 0. If you plug in 3, something positive, right? Okay, that's all what we're really looking for, right? We're just looking for the positive or negative nature of the answer. So based off of these critical points evaluated in the second derivative, we can use these results to help us determine if these are maxes, mins, or neither. Maybe they're not a critical point, so or a max or min. What do we think about the critical point of 0? Max or min or nothing based off of this second derivative result? Nothing. Okay, if the second derivative is 0, that's telling you you don't have any curvature at this spot. You're not concave up or concave down. You're kind of straight, okay, like a linear path. So we'll say x equals 0 is not a max slash min because the second derivative was 0. Yeah.
I'm a little off the path here.
Okay.
So that when we took the critical points of the first derivative.
Yep.
And then on the other page, did we do the same thing or did I write it down wrong?
So we assumed that x equals a is a critical point. So this would come from the first derivative like we did.
So I was talking about the one on
Up
top.
here?
Is that a whole different thing?
This is a different thing. So we found the second derivative and set it equal to 0. That would give us possible inflection points. If you were to set the first this equation equal to 0, those would give you your critical points.
Okay, so on that one, we're looking for concavity and stuff.
This is concavity,
And then on the other page, we are looking for.
maxes and mins.
Okay.
Okay? But we're using concavity in this case to help us verify maxes or mins. So it's a kind of a merger of the two. Okay? So even though 0 was a possible critical point, or a possible max or min, the second derivative test verifies that it's not. Can you think about what's happening here at 0? What was one of the cases when we did the table, if it was a critical point but it wasn't a max or a min? Yeah? It's level. Okay, so you have something level here. If you're level, for instance, like this, okay, you don't have any curvature right there because you're flat. You're not concave down or concave up. So that's what this is telling us. You have no curvature. What about x equals 3? Max, min, or nothing? If the second derivative is positive, then f of x is concave up. So you have a minimum. Okay, so this is where it's tricky. Notice how this result is positive. You might think max, right? But it's actually a minimum. This result is curvature. not maxes or mins. So x equals 3 is a minimum because the second derivative is positive. Okay, so find the critical points, just like you normally would for a sign chart, but instead of doing the sign chart, which you definitely could do, this is an alternative method. Do we think it's kind of quicker? You're plugging in a number and you're just looking at the answer, and that's telling you basically max or min right there. Okay, we'll go ahead and save number 2 for tomorrow just as a warm-up. So we'll stop there for today.